Today we start the next lecture of the complex number. Yesterday we have studied about what is complex number, what is imaginary part, what is real part of a complex number. Also we have studied about equality of complex number and the operations on complex number. And also we have studied about polar form of a complex number in which we talk about the amplitude and argument, amplitude or argument, both are same, and modulus of a complex number. So today we start the properties of complex number, properties of arguments. First one, the argument of the product of two complex numbers of the product of two complex numbers is equal to sum of their argument. That is to say argument of Z1 into Z is equal to argument of Z1 plus argument of Z. Second one, the argument of the quotient of complex number is equal to the difference of their argument. Is equal to the difference of their argument. It means argument of Z1 upon Z2 will be argument of Z1 minus argument of Z. Third is that argument of Z to the power n will be n into argument of Z. Fourth one, argument of Z bar will be minus of argument of Z. Fifth one, argument of 0 is not argument of 0. It's not defined. So these are the properties of argument. So if we have want to prove these one, means if we have first one that argument of Z1 times argument of Z2 equals argument of Z1 plus argument of Z. So how can we prove it? We know the general form. In polar form, the complex number can be written as Z equals R e to the power I theta. So let us take We have two complex numbers, Z1, which is R1 e to the power I theta 1, and Z2, which is R2 e to the power I theta 2. Now, then argument of Z1 into Z2. We have to prove firstly I can write argument of Z1 H theta 1 and argument of Z2 is theta. Now we have to prove that argument of Z1 into Z2 will be argument of Z1 plus argument of Z. So it will come argument of Z1 into Z2 will be theta 1 plus theta. That is argument of Z1 plus argument of Z. We can solve it easily, means we can prove it. How we can prove? Argument of this one, Z1, Z2, means Z1, Z2 will be R1, R2, e to the power I theta 1 plus theta 2. So argument of it will be argument of Z1, Z2 will be theta 1 plus theta 2, and we know our theta 1 is argument Z, Z1 plus theta 2 is argument of Z. So hence true. Second one, if we want to prove argument of Z1 upon Z2 will be argument of Z1 minus argument of Z2. So how can we prove? So now Z1 upon Z2 will be R1 e to the power I theta 1 upon R2 e to the power I theta 2. So it will come R1 upon R2 e to the power I theta 1 minus theta. So this implies that argument of Z1 upon Z2 will be theta 1 minus theta 2. And we know theta 1 is argument of Z1 minus argument of Z. So hence we can say argument of Z1 upon Z2 will be equal argument of Z1 minus argument of Z. Remember one thing, if argument of Z equals theta, then theta is not unique. So 2n pi plus theta, 2n pi plus theta is also argument of Z. So when where n is 0, plus minus 1, plus minus 2, plus minus 3, and so. So these are the proof how we can prove argument of Z1 times Z2 will be argument of Z1 plus argument of Z2. Likewise, argument of Z1 upon Z2 will be argument of Z1 minus argument of Z2. Now there are some results. First one, argument of 0 is not defined. Second one, argument of positive real number is 0. For example, or it can be written as 4 to the power I 0. So here theta is 0 means argument of 4 is 0. Third one, argument of negative real number is plus minus pi. Number is plus minus pi. If we have minus 5, so it can be written as 5 to the power plus minus I pi. Because we know that e to the power I theta means cos theta plus iota sine. So it means e to the power plus minus I pi will be cos pi plus minus I sine pi plus minus. And you know cos pi is minus 1. So that's why we can write it like that. So the argument of negative real number is always plus minus pi. Or argument of I base pi by 2 if b is greater than means argument of I is pi by 2. Yeah, we can say 2i, 3i, 4i. All these are pi by 2. The next one, argument of z bar is minus of argument of z. Now we go for some example. So we have example 1. Argument of z plus argument of z bar is 2 and pi, where n is an integer or 0. So first we have argument of z plus argument of z. We know that argument of z plus argument of z means argument of z times z bar. We know that value of z is r e to the power I theta, and value of z bar will be r e to the power minus I. So it will come argument of r square e to the power 0 I. That is, we can write argument of r square So this is possible. So it is 2n. For r square, we can write it r square e to the power I0. The general value is given by theta equals 2n pi plus minus alpha. This is equal to n pi plus minus 0 or theta equals 2n pi. So this is the answer. Now we move to next. Proof that argument of z minus argument of minus z will be plus minus pi. Solution. We know that argument of z1 upon z2 will be argument of z1 minus argument of z2. And we know that argument of minus c is plus minus pi, where c is any positive number. So in this view, we get argument of z minus argument of minus z will be argument of z upon minus z. So this is argument of minus 1, and we know that the argument of negative real number is plus minus pi. So hence we prove that argument of z minus argument of minus z will be plus minus pi. So this is the answer. So now we move to next one. Polar form of a complex. Here complex number is given minus 5 plus 5 pi. So we know that the polar form of a complex number is z equals r e to the power I theta, where r is the modulus, means the square root. This can be if we have z equals x plus iy, then r will be square root of x square plus y square, and theta will be tan inverse y upon x. And here there is a direct polar form z equals r cos theta plus I sin theta. So we can find modulus of it like that 5 whole square plus 5 whole square. So it will be 5 root 2. Now we have 5 plus 5 pi. We can write it 5 or minus 1 plus I. So this will be From this, we can get the value of modulus is this, and value of tan theta will be 5 upon minus 5. This is theta equals minus 1. Tan theta equals minus 1, so theta equals tan inverse 1 minus 1. That is plus minus pi by. It will be minus pi by. Now we can put the value of these. This is 5 root 2 cos minus pi by 4 plus sine minus pi by 4. This is um, tan inverse minus 1, that is tan pi minus pi by 4, that is 3 pi by 4. And we know that this is minus 1 by root 2 and this is plus 1 by root 2. So the polar form will be 5 root 2 e to the power 3 pi by 4i. This is the correct answer. The next example is A and B be two complex numbers. Let A and be two complex numbers such that A upon B plus B upon A will be 1. Prove that origin and two points represented by A and B. Prove that origin and 2 points represented by A and B form vertices of an equilateral triangle. Solution that this is origin, this is first point, its position is P of Z1, second point is P of Z2. So let us write OP will be alpha. This is Z1 minus 0. PQ will be beta, that is Z2. So this is Z2 minus Z1 and QO. This is gamma equal to 0 minus Z2. Then alpha plus beta plus gamma will be Z1 plus Z2 minus Z1 minus Z2, that is 0. Likewise, alpha bar plus beta bar plus gamma bar also will be 0. Also, triangle is equilateral, so all its sides are equal. triangle is equilateral. OP whole square will be PQ whole square equals QO whole square. So this is alpha square equals beta square equals gamma square. Alpha square means alpha alpha bar, beta beta bar, gamma gamma bars equals K. So from here we get alpha bar is K upon alpha. So K upon alpha plus K upon beta plus K upon gamma. Just put the value in this equation where we write this one. Alpha plus beta plus gamma equals 0. And this is 2. So just put in 2. We get this equal 0. So it means 1 upon alpha plus 1 upon beta plus 1 upon gamma equal 0. Just put the value of all these. Here the value of alpha is Z1, value of beta is Z2 minus Z1, and value of gamma is Z2. So just solve it. So what we get? Z2 minus Z1 times Z2 plus Z1 Z2 minus Z1 Z2 minus Z1 equals 0. So from this we can simplify it Z2 square minus Z1 Z2 plus Z1 Z2 minus Z1 Z2 minus plus Z1 square equal 0. So this is cancel out. We get Z2 square minus Z1 Z2 plus Z1 whole square equal 0. If we divide it by Z1 Z2, so we get divided by Z1 Z2, so we get Z2 upon Z1 minus 1 plus Z1 upon Z2 equal 0. So it will come Z2 by Z1 plus Z1 by Z2 equal 1. And Z1 we can write A upon B plus B upon A equal 1. Hence, so this is the solution. The next is very important question and very easy question. What is wrong with the following? If we have 1 equal square root of 1, then we can write it minus 1 into minus 1, and we know that square root of minus 1, we can write it like that, and this is I times I, so this is I squared, and its value is minus 1. So what is the problem here? Square root of -1 times minus square root of 1 is not correct because for square root of a times square root of b will be square root of ab if at least one of a or b is positive. One of a or b is positive. So this is the solution. Now we move to next. If Z1 and Z2 are two non-zero complex numbers such that modulus of Z1 plus Z2 will be modulus of Z1 plus modulus of Z2. Then find argument of Z1 minus argument of Z2. Z1 plus Z2 का modulus equal modulus of Z1 plus Z2. So we know Z1, we can write Z1 equal to X1 plus IY1, Z2 equal to X2 plus IY2. So if we put the value of these, so it will be X1 plus IY1 plus X2 plus IY2 equal X1 plus IY1 plus X2 plus IY2. So it can be written as x1 plus x2 plus iota y1 plus y equal x1 plus iy1 plus x2 plus iy2. So it can be written as square root of x1 plus x2 whole square plus y1 plus y2 whole square. And this will be equal x1 square plus y1 square and likewise square root of x2 square plus y2 square. Now squaring both the sides. So what we get? X1 plus x2 whole square plus y1 plus y2 whole square equal x1 square plus y1 square plus x2 square plus y2 square. This is now we can also open these. We can open it. So we get x1 square plus x2 square plus 2x1 x2. Likewise, y1 square plus y2 square plus 2y1 y2. So it will be x1 square plus y1 square plus x2 square plus y2 square plus twice of square root of x1 square plus y1 square times square root of x2 square plus y2 square. So this is cancel out, this is cancel out from here. So what we get? 2, we can take 2 as common. So x1, x2 plus y1, y2 equals 2 times square root of x1 square plus y1 square times x2 square plus y2 square. Now squaring this can be cancelled out and squaring both the sides. Squaring both the. So what we get? Yes. Squaring both the sides, so we get x1 x2 plus y1 y2 whole square equals x1 square plus y1 square x2 square plus y2 square. So it will be x1 square x2 square plus y1 square y2 square plus 2x1 x2 y1 y2 equal. We get x1 square y1 x1 square x2 square x1 square y2 square y1 square x2 square plus y1 square y2 square. So it will be y of x1 x2 y1 y2 will be x1 square y2 square plus x2 square y1 square. Now we can solve it. We can write it like that x1 square y2 square y plus x2 square y1 square minus twice of x1 x2 y1 y2 equal 0. So it will come x1 y1 plus x2 minus x2 y2 y1. Sorry, x1 y2 x2 y1 का whole square equal 0. So this implies x1 y2 minus x2 y1 equal 0. So we get x1 upon x2 equal y1 upon y2 equal k. Now we say it is real. So we can write it. This implies z1 equal x1 plus I y1 equal k times x2 plus I y2. Means we can write kz. So this Argument of Z1 minus argument of Z2 is argument of Z1 upon Z2 will be argument of KZ2 upon Z2 will be argument of K. So the value of argument of Z1 minus argument of Z2 will be, it will be 0 and pi and minus. Holding K is greater than 0 or K is less than 0. Means if K is greater than 0 then it is 0, and if K is less than 0 then it is plus minus pi. As we know, the argument of any real number is of 0. Also argument of any negative real number is plus minus pi. So these concepts are used in this question. So I think I did enough for today. So we will continue tomorrow.